What is up, y'all? Today I'm going to be watching another MIT video. I know it's been a while since my last one, but I'm here. Alright, so I think the way to do it, we'll go on YouTube again. Okay, we're jumping straight in. And let me see if I can get the chat over here, this side. Ooh, y'all might be able to hear the video. I didn't think. Let's see. Oh yeah, yeah. Blue stacks. Thank you for that, Rifford. Okay, I can finally see the chat now. All right. All right, I'm gonna take a quick break from this. I actually have to move a chemical. So yeah, the plan is this kind of next week is to actually write out some times that I stream, so I don't just like go on a hiatus constantly. Um, because one thing is I had class, so now I don't have class, and I should be able to focus a little more on it. But here we go. I'll show you what I'm doing. So I'm in a lab today, and I'm moving these tissue samples into increasing amounts of ethanol. Clock. So, yeah. Pretty exciting stuff. It's about as exciting as watching paint dry for a couple hours, but you know, you don't have to watch it. You can kind of do other stuff as it sits in these liquids. Uh, and what it's doing in these liquids is really interesting. So the liquid water in the head is being replaced with ethanol. So I'm putting it in increasing amounts of ethanol, which is another liquid that is going to replace the water. And then through a series of other liquids that I'm putting it through, eventually we'll have kind of replaced the water in the heads in these tissue samples, which they're fish heads. A little dark, but yes, going back. We're replacing the water in the fish heads with wax, and then eventually going to embed these puppies, well, fishies, into some wax and slice up their brains. All in the name of science, and hopefully we find something, you know, unique and new in our data. Anyways, thought I would start sharing this science stuff a little bit too. This is pretty much what I've been doing for a while, and I figured I'd just start streaming it. Like, I mean, sometimes there's people in the lab room here, so it's like I don't wanna be streaming and like bugging other people while they're in here, but I don't know. Nobody's here. Kind of just chilling. Kind of a fun thing to do. That's my thought behind it, at least. Anywho. Oh, is my desktop audio muted? But that might not be great. Send me the video. Can I be heard? We'll figure that out. If so, the last 20 minutes of video stream was probably abhorrent. Well, got this done. Yes. Okay. All right, moving back. These chairs are really short. Oh my god. I don't know. Anyways, that was a wonderful little falling out of my chair moment I just had. Okay. I'm just gonna continue watching this dang video. Where'd my phone go? Whatever. Chat. They chatting. They chatting. They chat. Okay. Oh, -10. Oh, it's all for Y. Okay, that's
Okay, I want to use that.
Oh.
Okay, now, so my question is, what's the matrix
This
that
whole
does
stream has
this
been silent.
first step? That
Whoops.
subtracts 3 of equation 1 from equation 2. That's
I
what I
should have
want to
double
do.
checked that after I said that.
So this is going to be a matrix that's going to subtract 3 times row 1 from row 2. And leaves the other rows the same. I mean, the answer is going to be that. So whatever matrix this is, and you're going to like tell me what matrix will do it, it's the matrix that leaves the first row unchanged, leaves the last row unchanged, but takes 3 of these away from this, so it puts a 0 there, a 2 there, and a -2. Good. What matrix will do it? It's these. It should be a pretty simple matrix because we're doing a very simple step. We're just doing this step that changes row 2. So actually row 1 is not changing. So tell me how the matrix should begin.
So for this.
1. So the first row of the matrix will be 1, 0, 0. Because that's just the right thing. That takes 1 of that row and none of the other rows, and that's what we want. What's the last row of the matrix? 0, 0, 1. Because that takes 1 of the third row and none of the other rows. That's great. Okay. Now, suppose I didn't want to do anything at all. Suppose my row, well, I guess maybe I had a case here when I already had a 0 and didn't have to do anything. What matrix does nothing? Like just leaves you where you were. If I put in 0, 1, 0, that's the matrix. What's the name of that matrix? The identity matrix, right. So it does absolutely nothing. It just multiplies everything and leaves it where it is. It's like a 1, like the number 1 for matrices. But that's not what we want, because we want to change this row 2. So what's the correct? What should I put in here now to come out to do it right? I want to get, what do I want? What am I'm after? I want to subtract I want 3 of row 1 to get subtracted off. So what's that row, what's the right matrix to finish that matrix for me? -3 goes here. And what goes here? That 1. And what goes here? The 0. That's the good matrix. That's the matrix that takes -3 of row 1 plus the row 2 and gives the new row 2. Should we just like check some particular entry? How do I check a particular entry of a matrix in matrix multiplication? Like suppose I wanted to check the entry here that's in row 2, column 3. So where does the entry in row 2, column 3 come from? I would look at row 2 of this guy and column 3 of this one to get that number. That number comes from the second row and the third column, and I just take this dot product, -3, I'm multiplying, -3 plus 1 and 0 gives the -2. Yeah, it works. So we got various ways to multiply matrices now. We're sort of like informally. We've got by columns, we will have by columns, by rows, by each entry at a time. But it's good to see that matrix multiplication when one of the matrices is so simple. So this guy is our elementary matrix. Let's call it E for elementary or elimination. And let me put the index as 2, 1, because it's the matrix that we needed to fix the 2, 1 position. It's the matrix that we needed to get this 2, 1 position to be 0. Okay, good enough. So what do I do next? I need another matrix, right? I need to, there's another step here, and I want to express the whole elimination process in matrix language. So tell me what now, so next step, step 2, which was what? Subtract, what was the actual step that we did? I think I subtracted, do you remember? I had a 2 in the pivot and a 4 below it, so I subtracted 2 times row 2 from row 3. From row 3. Tell me the matrix that'll do that. And tell me its name. Okay, it's going to be E for elementary or elimination matrix. And what's the index number that I use to tell me what? E32, right? Because it's fixing this 3, 2 position. And what is the matrix now? Okay, you remember, so E32 is supposed to multiply my guy that I have, and it's supposed to produce the right result, which was it's supposed to leave the first row, it's supposed to leave the second row, and it's supposed to straighten out the third row to this. And what's the matrix that does that? 1, 0, 0, right? Because we don't change the first row. And the next row we don't change either. And the last row is the one we do change. And what do I do? Let's see, I subtract 2 times, so what's this row? What's this here? 0, right? Because the first row is not involved. The second, it's just in the 3, 2 position, isn't it? The key number is this minus the multiplier that goes sitting there in that 3, 2 position. So is it a -2 to subtract 2, and then this is a 1, so that the overall effect is to take -2 of this row plus 1 of that. Okay. So I've now given you the pieces. The elimination matrices, the elementary matrices that take each step. So now what? Now the next point in the lecture is to put those steps together into a matrix that does it all and see how it all happens. So now I'm going to express everything we did today so far on A. Was to start with A, we multiplied it by E21, that was the first step, and then we multiplied that result by E32, and that led us to this thing, and what was that matrix? U. You see why I like matrix notation, because they're in like little space, a few bits when it's compressed on the web, is everything, is this whole lecture. Okay. Now, there are important facts about matrix multiplication. And we're close to maybe the most important. And that is this. Suppose I ask you this question. Suppose I start with a matrix A, and I want to end with a matrix U, and I want to say, what matrix does the whole job? What matrix takes me from A to U, using the letters I've got? So, and the answer is simple. I'm not asking this, but it's highly important. How would I create the matrix that does the whole job at once, that does all of elimination in one shot? It would be, I would just put these together, right? In other words, this is the thing I'm struggling to say. I can move those parentheses. If I keep the matrices in order, I can't mess around with the order of the matrices, but I can change the order that I do the multiplications. I can multiply these two first. In other words, you see what those parentheses are doing? It's saying multiply the e's first, and that gives you the matrix that does everything at once. Okay. So this fact, that this is automatically the same as this. For every matrix multiplication, which I'm conscious of still not telling you in every detail, but like you're seeing how it works. And this is highly important, and maybe tell me the long word that describes this law for matrices, that you can move the parentheses. It's called the associative law. I think you can now forget that. But don't forget the law. I mean, like, forget the word associative. I don't know. But don't forget the law. Because actually, we'll see so many steps in linear algebra, so many proofs even of main facts come from just moving the parentheses. It's like, and it's not that easy to, I mean, to prove that this is correct, you have to go into the gory details of matrix multiplication, do it both ways, and see that you come out the same. Maybe I'll leave the author to do that. Okay, so there we go. That's how so there's a single matrix. I could call it E. Now, while we're talking about these matrices, tell me there's another type of elementary matrix, and we already said why we might need it. We didn't need it in this case, but it's the matrix that exchanges two rows. It's called a permutation matrix. Can you just tell me what that would be? So I'm just this is a slight digression, and so let me figure out where I'm going to put a permutation matrix. You'll see I'm always squeezing stuff in. So permutation. Or in fact, this one exchange rows. Shall I exchange rows 1 and 2 just to make life easy? So if I had my matrix, let me just do 2 by 2, A, B, C, D. Suppose I want to find the matrix that exchanges those rows. What is it? So the matrix that exchanges those rows, the row I want is CD, and it's there. So I better take one of it. The row I want here is up top, so I'll take one of that. So actually, I've just the easy way. This is my matrix that I'll call P for permutation. It's the matrix. Actually, the easy way to find it is just do the thing to the identity matrix, exchange the rows of the identity matrix, and then that's the matrix that'll do row exchanges for you. Suppose I wanted to exchange columns instead. Columns have hardly got into today's lecture, but they certainly are going to be around. How could I, if I started with this matrix A, B, C, D, then I wouldn't, I'm not even going to write this down. I'm just going to ask you. Because in elimination, we're doing rows. But suppose we wanted to exchange the columns of a matrix. How would I do that? What matrix multiplication would do that job? Actually, why not? I'll write it down. So this is like just, I'll write it under here and then hide it again. Okay, suppose I had my matrix A, B, C, D, and I want to get to AC over here and BD here. What matrix does that job? Can I multiply, can I cook up some matrix that produces that answer? And you can see from where I put my hand, I was really asking, can I put a matrix here on the left that will exchange columns? And the answer is no. So I'm just bringing out again this point that when I multiply on the left, I'm doing row operations. So if I want to do a column operation, where do I put that permutation matrix? On the right. If I put it here, where I just barely left room for it, so I'll exchange the two columns of the identity, then it comes out right. Because now I'm multiplying a column at a time. This is the first column and says take none of that column, one of this one, and then you got it. Over here, take one of this one, none of this one, and you've got AC. So, in short, to do column operations, the matrix multiplies on the right. To do row operations, it multiplies on the left. Okay. Okay. And it's row operations that we're really doing. Okay. And of course, I mentioned in passing, but I better say it very clearly, that you can't exchange the orders of matrices. And that's just the point I was making again here. A times B is not the same as B times A. You have to keep these matrices in their Gauss-given order here, right? But you can move the parentheses. So that, in other words, the commutative law, which would allow you to take it in the other order, is false. So we have to keep it in that order. Okay. So what next? I could do this multiplication. I could do E32. So let me come back to see what that was. Here was E21. And here is E32. And if I multiply those matrices together, E32 and then E21, I'll get a single matrix that does elimination. I don't want to do it that way. I don't. If I do that multiplication, there's a better way to do this. And so in this last few minutes of today's lecture, can I anticipate that better way? The better way is to think not how do I get from A to U, but how do I get from U back to A? So reversing steps is going to come in. Inverse, I'll use the word inverse here. Okay, so let me make the first step at what's the inverse matrix. All the matrices you've seen on this board have inverses. I didn't write any bad matrices down. We spoke about possible failure, and for a moment we put in a matrix that would fail. But right now, all these matrices are good. They're all invertible. And let's take the inverse. Well, let me say first, what does the inverse mean, and find it. Okay, so we're getting a little leg up on inverses. Okay, so this is the final moments of today. Ah, sorry, he's still there. Okay, inverses. Okay, and I'm just going to take one example and then we're done. The example I'll take will be that E. So my matrix is 1, 0, 0, minus 3, 1, 0, 0, 0, 1. And I want to find the matrix that undoes that step. So what was that step? The step was subtract 3 times row 1 from row 2. So what matrix will
Oh, I have no idea.
get me back? What matrix will bring back, you know, if I started with a 2, 12, 2 and it changed it to a 2, 6, 2 because of this guy, I want to get back to the 2, 12, 2. I want to find the matrix which undoes elimination, the matrix which multiplies this to give the identity. And you can tell me what I should do in words first, and then we'll write down the matrix that does it. If this step subtracted 3 times row 1 from row 2, what's the inverse step? I add 3 times row 1 to row 2, right? I add it back. What I subtracted away, I add back. So the inverse matrix in this case is, I now want to add 3 times row 1 to row 2. So I won't change row 1.
Something like that.
I won't change row 3. And I'll add 3 times row 1 to row 2.
Yeah, that makes sense.
That's a case where the inverse is clear. It's clear in words what to do. Because what this did was simple to express. It just changed row 2 by subtracting 3 of row 1. So to invert it, I go that way. And if we do that calculation, 3 times this row plus 1 times this row comes out the right row of the identity. Okay, so inverses are, and so if this matrix was E, and this matrix is I for identity, then what's the notation for this guy? E to the minus 1, E inverse. Okay, let's stop there for today. That's a little jump on what's coming on Monday. So, see you Monday.
All right. See you Monday, Prof. Okie doke. I'll do one little thing in the lab here, and then I'll call it a day. All right. So I'm going to go back and move a couple more samples into a higher percent ethanol. That's basically it. I'll go back to this little scene here and try not to break something. All right, so I'm going to move these to this, and I'm going to fill this up real quick. Alright. Think, Mom. Get this back. This is such a funky. And we're just moving these and moving these and moving this. It's pretty relaxing once you get a nice little groove with this kind of stuff. The science can be kind of interesting too. So that kind of helps with the monotony of doing this over and over and over. I know most of that probably didn't make sense. Anyways, I've basically given a little sneak peek into what I do in the labs and stuff. There's definitely days that are more exciting than this, I promise. But sometimes you really are just moving something from liquid to liquid and calling it a day. Then you go home and you eat and sleep and you wake up and do it again. Or you don't. Or you just take a little chill day. Alright. Final one. Boom. Close this up. Then we're good to go. Set a 30-minute timer. Set a 30-minute timer. Okay, y'all. That was pretty much the entire stream. At least that's all I have planned for today. So, yep. Have a good day and peace out. Hi, Richard.